We are given the equation of the curve C. It is y is equal to x squared plus 5 divided by x minus 2. And what we are supposed to prove is that there exists two values such that the curve C cannot lie between. And to do that, I'm going to improvise by introducing a horizontal line, y is equal to k. And I'm going to prove that there exists value of k such that this horizontal line will not cut the graph at all, which means that we will be able to prove that C cannot lie between some values, and hopefully there are two values. And we hopefully can also determine the two values along the way. So what I'm going to do is I'm going to solve this as a pair of simultaneous equations, since we are talking about the intersection between this graph and this graph. So I'm going to let equation number 1 be equal to equation number 2 to solve for the intersection, which means that I have an x squared plus 5 divided by x minus 2. This is equal to k. Cross multiplying this, we have this plus 5 is equal to kx minus 2k. Moving everything over to the left hand side. So it is x squared minus kx plus 5 plus 2k. This is equal to 0. And do we actually want a solution to this equation? We don't want a solution, because we are trying to show that it is possible for k, y equal to k, it is possible for us to find a value of k such that there is no solution to this, such that there's no intersection between this graph and this graph. So I'm going to let the discriminant, since we are getting a quadratic equation over here, I'm going to let the discriminant be less than 0, so that this quadratic equation will have no solution. And that is b squared minus 4ac. So I have this to be less than 0. Let's see whether we can solve for some values of k through this. So this is going to be k squared minus 4 times 2k. This gives us minus 8k. And this gives us minus 20. This is less than 0. Factorizing this, we have a k minus 10 and a k plus 2. This is less than 0. Solving this quadratic inequality, I'm going to draw a k-axis, and the graph is going to be like this. Graph of the left hand side, this value here is minus 2, and here is equal to 10. And this is the region where this is less than 0. So we can see that k is going to be between minus 2 to 10, which means that as long as y is between minus 2 and 10, this and this will have no intersection, and hence we have proven that C cannot lie between two values. Let me write it down here. Therefore, C cannot lie between two values. Cannot lie between two values. And we can see what are the values. These two values are minus 2 and 10. We have to sketch curve C, and by looking at its equation, we can see that it has a vertical asymptote, and that is x is equal to 2. It is going to be having an oblique asymptote. To find out about the oblique asymptote, we're going to do a long division. I'm going to take x squared plus 5, which is x squared plus 0x plus 5, and I will divide this by x minus 2, and that is going to be x here multiplied by this. We have an x squared minus 2x. So 0 minus 2x gives me 2x. Then plus 5 here is going to be plus 2. Multiplied by this gives me this minus 4. Then this minus this is 9. So this can be re-expressed as x plus 2 plus 9 over x minus 2. And now with this new expression that we have come up with, we can know that the oblique asymptote is of the equation y is equal to x plus 2. And let me show you the graph that I have. My graph looks like this. Okay, so on my graph, I have my vertical asymptote x is equal to 2. I have my oblique asymptote y is equal to x plus 2. I've indicated the maximum minimum point. I've indicated the y-intercept. And if you were to look at the coordinates of the maximum minimum point, specifically the y-coordinate minus 2 and 10, these are the two values that we have proven in part 1 of the question. Because in part 1, we were trying to find the two values such that the curve will not lie between. So we can see graphically now that the curve cannot lie between this -2 and 10, which synchronize to what we algebraically determined in part 1 of the question. In part 3, we are going to be analyzing this equation, x squared plus 5 squared plus x plus 1 squared, x minus 2 squared is going to be equal to h squared times x minus 2 squared. We need to make use of the graph that we have generated in part 2, which bears an equation of this. So what I'm going to do is I'm going to take this equation, I will divide it by x minus 2 squared. So this divided by x minus 2 squared gives me a x squared plus 5 over x minus 2 squared. And this, please take note of it, this is the same as the right hand side of the equation of the curve C. And this plus this will be left with just this is equal to h squared. So now by looking at this equation and analyzing this equation over here, we can deduce the second graph that I'm supposed to superimpose on the graph that I have in part 2. This second graph will have the equation, second graph, it will have an equation of y squared plus x plus 1 squared is equal to h squared. Basically, I just replace this by y because I know that if I were to solve this and this as a pair of simultaneous equation, I will be getting this. Which means that if I have a graph of this, by sketching this on top of this, the x-coordinate of the intersection between the two graphs will represent the roots of this. And this graph that we are looking at, this second graph that we are looking at, it is one that is of a circle. It is going to be a circle with the center at -1, 0, and the radius is modulus of h. And -1, 0 is directly above the maximum point because it bears the x-coordinate of -1. So -1, 0 is, let's say, here. And if you were to think about it, if I were to sketch a circle, if I were to sketch a circle such that the circumference of the circle passes through the point 0 minus 5 over 2. So let's say it is here. Okay, so let's say the circle is somewhere here. Then the x-intersection, the x-coordinate of the intersection between this and the graph will be, one is negative, the other one is 0. But the question one of the roots to be a positive real number. So we don't have any positive real number for the x-coordinate yet until when the radius exceeds this distance here. Because the moment when the radius exceeds this distance from here to here, the moment when it exceeds, if I were to draw a circle that is bigger than this, can you see? If I were to draw a circle that is bigger than this circle, this dotted circle, then I will start to have a positive x-coordinate for the point of intersection. And this, because the x-coordinate of the intersection between the circle and this graph gives me the roots of this, which means that the moment when it is bigger than this dotted circle, I will be starting to get a positive real root, which means that in order for this to happen, we are going to let the radius, which is modulus of h, be bigger than this distance from here all the way until here. From here, the point, this point here is the point -1, 0 to this point here, which has this as the coordinate. So it is going to be bigger than the distance between these 2 points. So it will be -1 minus 0 square plus then 0 minus -5 over 2 square, the distance between 2 coordinate points. This tells me that modulus of h must be bigger than, this is square root of 29 over 4. And this will help us to solve for the value of h that the question wants. So for this, I'm going to square both sides. Squaring both sides gives me an x squared is bigger than 29 over 4. Cross multiplying and bring 29 over to the left hand side. We have a 4h squared minus 29. This is bigger than 0. Factorizing this, we have a 2h minus square root of 29 and 2h plus square root of 29. This is bigger than 0. If I were to sketch a curve where the horizontal axis is h, the curve is going to be something like this, where this here is minus square root of 29 over 2. Here is square root of 29 over 2. And since we are looking for the region that is bigger than 0, it is going to be this value of h and this value of h. So our answer is going to be h is supposed to be less than minus square root of 29 over 2. Or the other part of the answer will be when h is bigger than square root of 29 over 2.